Post at 661. Who knew that math can be fun? Odds, ratio, risk, difference. It's the bread and butter, baby, what's it doing?
Greetings, Bio 6611. In this lecture, we're going to discuss different types of observational study designs. We'll also introduce 2x2 contingency tables, a common and frequent way of summarizing data we might collect and get from an observational study. So let's start by defining the difference between an observational study and an interventional study. In an observational study, a researcher is documenting some naturally occurring phenomena, so the relationship between an exposure and an outcome. In other words, the researcher is not actively intervening. Exposure is already decided naturally or by some other lifestyle factors or situations. As an example, we might be looking at the incidence of cavities that occur in people who are ice cream eaters versus self-reported non-ice cream eaters. In contrast, though, we also have a world of interventional studies or experiments or randomized clinical trials where a researcher is actively performing some intervention. For example, maybe a researcher actually randomly assigns a group of people to eat ice cream every day for 1 month and another group to abstain from eating ice cream. Then at the end of that time period or at some later date, the researcher may assess the effect of ice cream eating on the risk of developing cavities. In addition to having this distinction between selecting or just observing an intervention of interest or exposure of interest, we also have to consider the timing of a study. And it turns out observational studies can either be prospective, retrospective, or cross-sectional. And so we can take a look at this figure here, which we'll revisit towards the end of this lecture, which just shows some of these different types of designs that we'll be breaking down in the following slides. So let's start with the prospective study. In this type of observational study design, we identify a group of disease-free individuals at what we might call our baseline. We'll then measure any exposures at baseline and follow these individuals over some period of time and to see if the disease develops or not. Oftentimes, the study population of interest is referred to as a cohort, and sometimes even more specifically, we'll call this a prospective cohort study to identify that we're starting at baseline with disease-free individuals, measuring their exposure, and then following them up to track disease status. For example, if we start with a group of individuals who have no cavities and we ask them if they regularly eat ice cream or not, we may follow them for 1 year then to see over that time period how many develop cavities based on that behavior. Now, less common, but also still possible, we can design prospective case control studies where controls are matched to cases as a case pops up or occurs in real time. So potentially we are identifying individuals who develop a cavity. We try to match those to individuals who would be controls who don't develop cavities. A retrospective study initially identifies 2 groups of individuals, a group that has the disease or the cases, and a group that does not have the disease or controls. We then look at the relationship between their prior exposures and disease status. Now, this is commonly known as that case control study. For example, we find a group that has those cavities or cases and a group that doesn't have the cavities, controls, and then we ask them about their past behaviors and habits over the previous year. Now, in this case, or situation I should say, cases are often matched to controls that are similar based on age, gender, or other features. Now, less common but also still possible is that we can design retrospective cohort studies, where subjects are selected based on their past exposure status, and then the researcher or researcher team will look at the outcome's current status at our present time. Finally, we can have a cross-sectional study. Now, this looks at the study population at a single point in time or a snapshot. All individuals are asked about their current disease status as well as their current exposure status. You may also have seen this called a prevalence study because the prevalence of the disease at any given time point then can be estimated between the exposed and unexposed individuals. For example, back to our ice cream example, we ask a group of people if they currently have cavities and if they are currently regular ice cream eaters. So returning again just to this graphic, we can see we have at the top here that cross-sectional, where we measure both the exposure and the disease at the same time in the present. We have this more case control, both retrospective and prospective, depending on the timing of measurement for the exposure and the disease status. We also have cohort studies, which can be retrospective, prospective, or, which we didn't mention before, ambispective, so spanning both past, present, and future. And we have then, of course, the interventional study designs where we actually actively intervene but didn't discuss necessarily in the context of this lecture. Now, one important thing to note is that many times these observational studies will result, based on the fact that we're measuring an exposure yes-no and a disease yes-no measure, in 2x2 tables to summarize our data. So with that, let's transition to discussing ways that we can structure this data for use in a future analysis. So we've already introduced previously in the semester various types of random variables and sample spaces and what they can observe. For example, they could be numeric or categorical. Numeric random variables can then be classified as either continuous or discrete, where a continuous random variable is something that could take any number on the number line. So for example, your height might be 5 feet 7 inches, or your weight might be 133.2 pounds. So it can be very precise, versus a discrete random variable can only take certain values, such as counting like a Poisson distribution, 0, 1, 2, 3, and so on successes. Now what we're focusing on here right now, though, is this lower bullet point for categorical random variables, which could be also themselves either ordinal or nominal. In the case of ordinal random variables, there's a meaningful ordering to the labels, and so they don't have a specific quantitative value, but we can order them as low, medium, or high. There's also nominal random variables, which have labels but no order. For example, the type of a dog breed, where we can't necessarily put them in any meaningful order just based on that information alone. Now, focusing more about nominal random variables, we have the situation in our 2x2 tables, or these observational study designs, where we have two possibly related nominal random variables, each having two categories. And this then can be represented in a 2x2 table, also known as a contingency table. For example, we might ask about lung cancer as our disease of interest and exposure as drinking status, whether you're a heavy drinker or a non-heavy drinker. We can see that if we design a study and collect the information, we can set it up in this 2x2 table where we can identify, for example, that yes, of 33 of the 1,700 individuals who are heavy drinkers went on to develop lung cancer. Now, more generally speaking, a 2x2 contingency table will often put the exposure or independent variable on the left-hand side, and then the disease status or the dependent variable at the top. The row and column sums are also shown here, where generically we can refer to this as A, B, C, and D for the number of observations we have in each given combination of exposure and disease. And we can see that we can combine things like N sub 1 and N sub 2 for the row sums, or M sub 1 and M sub 2 for the column sums. Now, oftentimes we're interested in actually estimating the probability of disease for those who were exposed versus unexposed to see if there might be some relationship or if it's a protective or harmful factor. And so we can note here that based on these summaries we have in this generic 2x2 table, we can calculate things like P sub 1 or P1 as an estimate of the probability of disease among those exposed, where we will take those who are both exposed and develop the disease divided by the total number of people exposed. Likewise, we can take this information and estimate the probability of disease among those who are unexposed by taking those who develop the disease but don't have the exposure, dividing by the total number of people who didn't have the exposure. In the next lecture, we're going to talk about the ways we can describe the behavior of P sub 1 and P sub 2 based on the risk difference, risk ratio, and odds ratio. It is useful and important to note here that P1, P2, RD, RR, and OR are all called statistics. They use the data to estimate the true probability parameters at that population level, but they themselves are an estimate or a statistic of our sample. And so with that, I look forward to discussing with you more in the next lecture on the ways we can actually measure these effects and show some examples.